Welcome back to Arts Learning. In this video, we're going to go over how to draw electric fields for 3 charges or more, okay? Because it does get complicated when you start mingling a lot of them. Before we start, this charge, this proton, has a charge of positive Q. This one also has a charge of positive Q. This one also has a charge of positive Q, okay? So that means that all of them has equal charges. So equal charge means the same amount of lines, right? Your lines are proportional, remember, proportional to your charge. So since we have the same charge, all our lines will be the same. We'll have the same amount of lines going into an electron or out of a proton. So accordingly, we can see that for this electron, we have 1, 2, 3, 4, 5, 6, 7 lines. For this proton, 1, 2, 3, 4, 5, 6, 7 lines. 1, 2, 3, 4, 5, 6, 7. There you go. Like all of them have the same lines. So that's the first thing you want to keep in mind. If you have a charge of 2Q, which I'll show you how to tackle in a bit, then you're going to have to accordingly increase your lines to 14. Okay? But here, for now, we keep it like it is. So then, what can we do? Well, looking at this, we know that before anything, we know that a proton makes lines outward, right? And we know that not all of those lines are gonna hit the electron. Some of them are gonna create their own field, right? So the field is the direction a charge would go, okay? A charge would go. So it really does depend on whether this is an opposite charge or an attractive charge, because if it was an opposite charge, then it could go in the opposite direction, which I showed you before, but right now let's just keep it like this, right? It's either that direction or completely opposite, but same thing. Would go if charge placed there, right? So with that knowledge, if you placed a proton here, it would move along that line, okay? If you placed an electron here, it would move along this line, but in the opposite direction, but same line. So how I drew this was, first for this electron, I drew these 7 lines, right? I decided that 3 of them would hit this electron, okay? From other spaces. It has it's emitting its own field, but this field isn't one that's interacting with these 2 protons, okay? It's emitting its own field. Think of it like that. And these 2 protons here, right? They're gonna emit their own fields. And I decided that each of them are gonna have 2 lines that hit the electron. So then this one accordingly is gonna have 2 lines, right? And the rest of the 5 lines, they create their own field. But you remember what I told you about protons repelling, right? Their lines are gonna look a bit like asymptotes. So they're gonna go close to each other, but they're not gonna hit each other. First off, lines can't hit each other. And second off, it's because they repel. So they go like that. Here, there's no repelling thing, so they can go straight, right? Or if I had a line, it could go straight a bit, but then slowly start tilting, curving, and hit the electron. But for now, I decided only 2 is fine, okay? Same thing here, all right? Okay. And then what happens is they repel at a certain point, right? Over here, if you place any charge here, an electron or a proton, it's not going to feel any force because there's no field there, right? And the second you place something there, if it is an electron, it would be attracted to both of them, okay? If it is a proton, it would be pushed away from both of them. So either way, they both cancel because it's at the same distance from both the protons, right? That's why this entire space is empty. Firstly, because we don't have enough field lines for that. I could use more, but also because at this point they repel. So there wouldn't be a field line, right? If there was a charge here, it wouldn't go in any direction. So then I can't have a field line because a field line is the direction the charge would go if it was placed there. If I don't have a direction, if I was placed there, I won't have a field line. Okay. So I wouldn't draw anything there. The asymptotes here, maybe a bit of curves here. So maybe I could go like that if I used more lines, but for now I'm not using more, right? And then the repel here. Okay. So this time was already pre-drawn, so maybe it might have been a bit easy for me, but now let me show you how to draw the field for this. Okay. So as you can see here, we need to sketch the direction for all these charges. I mean, not all of them, just a feel for these charges, okay? This one is -2 microcoulombs. This one is +2. And this one is +4 microcoulombs, which makes sense because it's twice as large, okay? So then I can decide how many lines is going to happen. Sometimes a given line, sometimes you can decide that, okay? I'm going to say for this electron, 6 lines. Okay, so for this proton, then it would be 12 because it's twice the magnitude. So then let me start drawing my field. So I could probably have, first let me write down 6 lines for each one. The electron, it goes inward, right? So first off, both these protons are going to hit this electron. So there we go. That's 2 of my lines. And then there's also more lines like that. They could, go like that. You also want to make sure you always fill the page, okay? This is very important, don't forget. Fill the page when you're given an electric field. Unless they tell you it's not. I mean, you don't need to. You do get points off if you don't fill the page. So always make sure you fill the page with your fields and your arrows, okay? And then maybe one goes super long, like that. Similarly, one goes super long, like that, okay? And then from that, we have our electron attracting both adequately, okay? Maybe, actually, let me make this 8 lines because I want to show you some more stuff. So then at this point here, this proton would go like that, it would go here, right? Lines don't touch, remember? Same thing here, they wouldn't touch, but they would still attract to the same position. There'd be no field here because they equally repel or equally attract. And then we draw it for the proton. So I drew 8 lines for the electron. This proton has 4 lines. I need to draw 4 more lines, right? So let's see, how would I draw 4 more? I can curve. So you want to keep in mind, right? The reason this curves is because if you extend this curve long enough, it's eventually going to come back like that, back toward the electron. But you don't need to draw it that long, okay? Just curve it for the sake of curving it. I'm just saying why you would think it curves. So then, same here. 1, 2, 3, 4, 5, or, well, still sits, so I have 2 more to go. Then I'd probably put one bit straight but bit curved here. I have 7. So then one more could probably go like that. Okay. Actually, this field is going to be overwhelmingly dominated by the larger magnitude charge. So I'm going to draw it more like that. Okay. So then since each one gets 8 lines, since this is twice as large, it's going to get 16 lines. Okay. So I have 4 lines here, but I need 12 more lines. So a lot of lines, right? So I would keep it curved like that. More. And the reason I also didn't connect it, one more reason, is because then, the electron is confined by 8 lines, right? So if you had more lines in handy, then you could probably curve it and draw the super curve, but you don't need to do that because first off, not all curves connect to the electron, and second off, you don't have enough lines for that. Okay, so here we go. This is our 5th line, or 6th line, or our 7th line, our 8th line, our 10th line, and our 11th line, and our 12th line. So you see why I drew these more to the right than this to the left? Because since this charge is larger, its field lines are going to kind of dominate this space a bit more. And it's going to push this charge back. But there you go. Looks pretty nice, right? Fascinating. All these electric and gravitational fields. Gravitational fields will go over next video, but there you go. This point P is a null point. It has to be closer to the, so it should be given the electron here, the proton here, and this, you don't need to worry about that too much, but this is how the fields work. But if you did place, so for example, if you, actually let me draw this line a bit better, because this is going to dominate in every aspect. It's always going to push this proton back because it has a larger magnitude, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, so maybe I didn't draw the 12th line. There you go. Okay. And then if you placed a point P here, where is it going to go? It's going to go in this direction, right? It's going to be attracted. So it depends on whether point P is an electron or proton, but if it's a proton, it's going to be repelled in this direction. Okay, so let me draw this in a different color. It's going to be repelled in this direction. But if it's an electron, it's going to be attracted along the same line. Like that. Okay, so not a great color, but you get the idea. All right, and then where are the field lines the strongest? So here, there are very dense lines, right? There's a dense spot. Where else? I mean, very close to the electron, it's all dense. So I would say dense here. Similarly, dense here. And then another spot you might have not thought of, like, so first, this is also going to be dense. But another spot you might have not thought of are these lines, right? They're kind of like asymptotes. So the closer they go to each other, the denser they get. And these go outward. So you can't end here and then say, oh, I end here, dense. Right? And the denser a field, the stronger that field is. So at those points, it'd be the strongest. Because the lines are the most closest together. All right, so now let's try a challenge. So here you have a challenge where you have an electron in the middle, okay? And 2 protons on the right of that electron. This one is a charge that's, let's just say this is 2q, this is q, this is negative q. So what direction is this electron going to go? I mean, you could use Coulomb's law, but that's not really needed here, right? You can know that the distance here between these two are the same because it's the same diagonal. So the force emitted is going to be along that distance. So for the proton, so think about the electron like that. This proton, right, is going to pull it towards it. So imagine this electron is going to be pulled towards it because of attraction, right? With the force of kq1, q2 over d squared, right? Or you don't even need to know all that. Just it's just force, right? Here, same thing happens, but it's going to pull. So, but k, this is 2q, right? So this is 2kq1, q2. So this is actually 2q1 or whatever, right? But same thing. And since q1 and q2, I could just write kq squared over d squared. And here, this would just be, so k times q1 times 2q1 over d squared. So just 2q1 squared k over d squared, right? So let me write that here. 2kq squared over d squared. So you realize how this force is twice as large, which makes sense, right? If you kept the distance the same, so if you remember Coulomb's law, right? If you kept the distance the same, But if you increased one of the charges by 2, then the entire thing gets doubled, right? It gets doubled. Because then it becomes 2kq1 q2 over r squared. And this is its own force. So then the force becomes 2 force. It doubles. So similarly, how am I going to draw that? The vector is going to be twice as large. Okay, so the vector is going to go 2 times longer. So I'm not going to get on my ruler and measure it, but it's going to be twice as long, okay? Because that indicates its magnitude. And then you can understand that if you were to draw these into components, so this time let me not pick a horrible color. Rightward here, upward here. So I'll say 1 up, 1 right, even though that's not true, but I'll just say that. Here this is 2 right? Because the force is twice as large. And this is 2 down. So this vector is going to oppose this vector, but in a certain way. So both of them are pointing right first. So this vector, it becomes 2 and 1. This vector becomes thrice as large, right? Because 2 plus 1 is 3. So it become very large. It become like that. Thrice as large to the right. Okay. And what about the vertical vector? So this one is 2 down, this one is 1 up. So they oppose each other, right? But since 2 down is larger, it's going to go 1 down. So, okay, that didn't look like 1, that looked like 2. Let's just draw 1 down. All right, and there you have it. So your net force would be, let me go back to my green color, this vector here. That would be your net force. Okay, so F net here, it's a bit wrong. I just meant that it's going to go in the right direction, thrice as long. This is actually F net. Okay, there you go. Next video, we're going to go over gravitational fields and how masses attract each other. So gravitational fields, every mass attracts each other, right? So we're going to go over what gravity actually means, because it's not the force of falling down, it's the force of attraction. And all masses attract each other. So literally you and the book, or you and the table, whatever you're writing on or whatever you're standing on, sitting on, they attract each other. You're attracting that. But similar to how the earth attracts you and how the sun attracts earth and sends it in gravitational motion. That's why when I was looking at planetary scales, I could equate the law of universal gravitation to the centripetal acceleration, right? Because gravity is a force of pulling, and pulling, it's the attraction. So the fields for gravitational are going to look a bit different. There is no repelling, and I'll show you what that looks like, okay? So stay tuned and make sure to check that out. Gravitational fields are cool.